This is your lesson on all the learning targets for complex numbers following the examples in Glencoe 5-9. We're first looking at the examples where there are square roots of negative numbers. In Algebra 2, you are now allowed to take the square root of negatives when evaluating expressions or equations. Now, they still do not appear on the Cartesian plane, which is why the graph of the square root function cannot produce negatives. Alright, so when looking at it, anytime we produce a negative underneath a radical, what this is actually going to cause us to pull out is an I, okay, because I is the imaginary unit. And so really then what we're left to simplify is the square root of 18. Well, 18, that's just going to be 9 times 2. That's why we're going to take the square root of both of those numbers. And the square root of 9 gives me a 3. I already have the I out there, and I'm left with a 2 underneath my radical. Alright, same goes for this guy here. Alright, we can automatically initially pull out the I, and then we know that 125, that's just going to be 25 times 5. So we're really dealing with the square root of 25 times the square root of 5, allowing for me to also pull out a 5. Okay, so far we have a 5i pulled out, with a square root of 5 left underneath my square root. Now we're dealing with x to the 5th. So we can remember our rational exponents, or we can simply remember that x to the 5th is really just x to the 4th times x. So we're dealing with the square root of x to the 4th times the square root of x. So we're going to leave x under the radical, and the square root of x to the 4th gets me x squared, leaving me with this expression here of 5i x squared times the square root of 5x. Alright, well, let's multiply some imaginary numbers now that we know what actually I is, okay? Alright, so just like we always do, we're always going to multiply our coefficients by one another. So negative 2 times 7 gets me negative 14. Now I'm looking at the I times the I. Think about it this way. I times I, that's really the square root of negative 1 times the square root of negative 1. The square root of a number times the square root of that same number is just going to produce whatever that quantity is underneath a radical, which is why I times I, which is I squared, is going to produce a negative 1, okay? So negative 14 times negative 1 leaves me with 14 as my answer. Now let's look over here. Another way of looking at it is we can just multiply the insides, okay? Or we can simplify them. They both allow us to pull out an I. So we're really dealing with I radical 10 times I radical 15. And I times I is going to get me I squared. So then we're going to have I squared times, well, 10 and 15. Let's break it down. 10 is 5 times 2, and 15 is 5 times 3. So let's start simplifying. I squared is negative 1. Notice I have two 5's up here, which tells me I can pull out a 5 outside my radical. And I'm left with a 2 and a 3, leaving me with a 6. So my final answer is going to be negative 5 radical 6. There are many ways of looking at how to simplify powers of I. One of the methods addressed in your textbook is just knowing your properties of exponents. But another way is using the quadrant method, okay? Where anything raised to what eventually is the first power is lying in the first quadrant where things are just equal to I, okay? Then in the second quadrant, we have all of our values of I squared, which is always going to be equal to negative 1, okay? Things in the third quadrant, I to the third, well, that's just going to be I squared times I, which will get me negative I. And then in our fourth quadrant, that's really going to be I squared times I squared, which is just positive 1. What you essentially can do here is figure out what portion of these exponents are the ones you're looking for. So what we can do is we take our exponent, and we're going to divide him by 4, okay? 45 divided by 4. What that's going to get me, well, 44 divided by 4 is a nice number of 11. So we're going to take 11 rotations around the quadrant circle. And then we're going to still rotate 1/4 of another way, which is why we're still going to end up in this first quadrant here, okay? Anything that ends up with this 0.25 lands in this first quadrant. If I added up with a 0.5, I'd end up with the second quadrant. So I to the 45th is just going to be equal to I. All right, now let's start solving some equations with imaginary solutions. Whenever we're solving equations, we're isolating our variables. So in this first equation, I'm just going to subtract 48 from both sides, getting me 3x squared equals negative 48. I'm now going to divide everything by 3, getting me, I forgot to change the exponent, wow. X squared is now going to be equal to negative 16. Whenever I take the square root of a quantity, plus or minus is always going to be in front because I could end up with a positive or negative quantity underneath the quantity being squared. When I take the square root of 16, that's going to produce I. Well, square root of negative 16 is going to produce an I, and the square root of 16 is going to produce 4. That's why my solution is plus or minus 4I. Now, let's look at a little bit more of a complex equation involving complex numbers where I'm trying to find the values of x and y that make this equation true, okay? So there's many ways of looking at this problem. Notice that this quantity of y minus 4, that's the only part that's going to be equal to the imaginary component of this equation. That's why I know that quantity y minus 4i, that's going to be equal to our quantity of 2i, okay? Just like the real portion, the guys that are not attached to an I, must be equal to the 3. So now I have both of these quantities set up to equal to what their parts are going to be, and I'm just going to solve. I'm going to add 3 and divide by 2. So 3 plus 3 is 6, and 6 divided by 2 is 3. Then over here, I'm going to divide both sides by I, leaving with y minus 4 equals 2. Then I'm going to add 4 and get y equals 6. Alright, we're almost done with complex numbers here, and I told you they weren't that scary. Alright, whenever adding or subtracting, just like we always do, we're always going to combine like terms, okay? In this scenario, the real component with the other real component. So here I'm adding, so I have 6 plus 1 is going to get me the real portion of this complex number. Now the imaginary portion will be the negative 4 plus the 3i. So negative 4i plus 3i is going to get me negative I. So my final answer in complex standard form is 7 minus I. Well, let's keep going. Now we need to remember that we're going to be subtracting. So we're going to have 3 minus 5. 3 minus 5 is going to get me negative 2. Now let's look at our complex portion. Negative 2i minus negative 4i. Notice that I articulate these things just so I make sure I'm noticing that a negative times a negative is a positive. So I really have negative 2i plus 4i, which gets me 2i. So my final complex number answer is negative 2 plus 2i. Alright, let's get into some multiplication. Now the thing we need to remember with multiplication is the fact that I squared is equal to negative 1. It's our big idea here. And in this real world problem, I'm given a value for I and a value for z, and I'm given this formula where I must multiply these two things together. So I'm going to take 1 plus 3. Well, j is just the electrical engineer's way of saying I. So you can really say whatever way you want. Let's leave it with I. Multiplied by 7 minus 5, again, let's just let it be I. Here we're going to have a binomial times a binomial, so we're going to FOIL. 1 times 7 gets me 7. 1 times negative 5i gets me negative 5i. 3i times 7 gets me 21i. And 3i times negative 5 gets me negative 15i squared. Now here's what we need to remember. This last guy here is really going to be negative 15 times negative 1, which is just going to be 15. So then we are going to combine like terms of 7 with negative or positive 15 getting me 22. The other things that are like terms are our negative 5i and our positive 21i. Negative 5i and positive 21i gets me 16i. So here is my complex number. Alright, the last operation to do with complex numbers is division. Alright, when we're simplifying our expressions, there's two scenarios. In A, we have a complex number on the bottom. Complex numbers are just like having radicals in the bottom. It's just simply not allowed. So we can multiply it by something. And the thing we're allowed to multiply it by is 1. But that's not going to get rid of I on the bottom. So we need to multiply it by something that'll get rid of the 2 plus 4i on the bottom, and that'll be its conjugate. So I'm going to multiply both the top and the bottom by its conjugate. Notice that a number over itself is equal to 1. That's why this is allowed. So on the top, I must distribute this 3i into this binomial here. If it was a binomial times a binomial, I would need to FOIL. So on the top, we end up with 3i times 2 is 6i. 3i times negative 4i gets me negative 12i squared. And we know I squared is negative 1. So this would give me a numerator of 6i plus 12. Now the denominator. The denominator is really just an example of a difference of squares. So one way of looking at it is just as a difference of squares. So the first term is 2, and the second term is 4i. So 2 squared is 4, and then we have 4i squared, that's going to be 16i squared, which is why this expression on the bottom just becomes 4 plus 16, which is 20. So in total, let me zoom out here. If we start simplifying it, the numerator was 6i plus 12, and it was all over 20. The only thing I can cancel out is common factors, okay? So I could just do a common factor, or I could break these things apart and give them their own denominators. So this is really going to be 6i over 20 plus 12 over 20. Well, 12 over 20, that simplifies to 3/5. And 6i over 20 simplifies to 3i over 10. Here we have it in standard form. Now what about scenarios where we're simply being divided by an I, like this guy here? We don't need to multiply by the conjugate. In fact, we don't even need to multiply by just the guy in the bottom itself. Whenever we only have an imaginary number in the bottom, all we need to multiply is I over I. Once again, because this is equal to 1, and you're allowed to multiply expressions by that. So then in the numerator, we're going to distribute the I into both terms in the top. So we get 5i plus I squared. I squared is just equal to negative 1, so we have 5i minus 1. Now on the bottom, 2i times I gets me 2i squared. Once again, I squared is equal to negative 1, so we have 5i minus 1 over negative 2. So one way, again, you can break this up is by giving each of them the denominator of negative 2. Okay? So we have negative 1 over negative 2, which becomes just a positive. So I'm just going to erase my signs there. And then we're going to have minus 5i over 2 because he was positive and he was negative. And so here is my complex number expression.